Imagine you're standing on a dealership lot, right? You're looking to buy a vehicle for your daily commute.
Yeah, just a regular A to B kind of car.
Exactly. But the salesperson, they walk you right past all the practical sedans and they stop in front of this absolute beast of a machine.
Like a hypercar.
Right. They point to the spec sheet and they highlight that this car is engineered to sustain, 180 miles per hour. It's got this carbon ceramic braking system designed for the Nürburgring and suspension tuned for high G cornering.
I mean, on paper, it sounds like an engineering marvel.
It is. Objectively, it is the best car on the lot. But then you have to stop and consider your actual daily reality.
Which is probably not the Nürburgring.
No, definitely not. You exclusively drive in a 30-mile-per-hour school zone, followed by, 20 minutes of brutal stop-and-go city traffic just to get to the grocery store.
Right.
So buying that car means you are paying this massive premium for high-performance capabilities, incredibly expensive maintenance schedules, and, complex proprietary parts that you will literally never, ever utilize.
It's a wildly impressive specification that is just completely divorced from your operational reality.
Exactly. And that disconnect.
That disconnect between theoretical maximum performance and actual operational need, well, that's the core of what we were unpacking today.
Welcome to the deep dive.
We are looking really closely at the paradox of precision today.
Yeah, because there is this natural, almost universally accepted instinct within engineering and procurement, right? To constantly demand the tightest tolerances, the most stringent safety margins, the most advanced materials available.
Right, because the assumption is always that pushing for the maximum specification inherently protects the project.
Yeah.
It feels safer.
But our sources today reveal how that exact instinct is quietly draining budgets, introducing massive delays, and ironically, making modern systems significantly more fragile and way less adaptable to change.
So our mission today is to really explore this concept of right-sizing.
We want to look at how matching the exact technical requirement to the current realistic operational environment is really the ultimate shortcut to efficiency and resilience.
And we have a really dense stack of sources today covering a huge spectrum of industries.
We really do. We're pulling research and case studies from manufacturing tolerances, aerospace engineering, defense procurement, pharmaceutical packaging, and even the gritty reality of casting floors.
All to prove why tighter or heavier or more stringent is, well, very frequently the enemy of better.
Taking a wide view across all these disparate industries, it really exposes a systemic issue, Over-specifying machines, processes, digital architectures, it creates this cascade of hidden costs that standard balance sheets almost never capture.
And we should clarify, we are not advocating for slashing safety protocol.
Oh, no, not at all. Not compromising quality either.
Right. We are analyzing how an unexamined, over-engineered solution transforms from a protective asset into a really severe logistical and financial liability.
Yeah. But before we get into the financial devastation of a bad specification, we really have to trace the origin of the problem.
Like, why does it happen in the first place?
Exactly. We are talking about decisions made by highly trained, incredibly intelligent engineers. So why do they default to the 180-mile-per-hour car for the school zone commute?
Well, research from Autodesk actually provides a really compelling look into the psychology and the mechanics of how engineering requirements are formulated.
Yeah, they point out that engineering teams almost never begin a project with a single coherent vision.
Or a neatly organized requirements package. The reality is that they start with highly fragmented inputs.
The front end of the engineering process is just chaotic, isn't it?
Oh, it's totally heterogeneous. The initial information an engineer receives is scattered across multiple incompatible formats.
Like what kind of formats?
Well, they might start with a vague narrative problem statement from a client's email, for example.
Right.
And then they have to combine that with a partial functional description from a marketing brief, maybe a handful of legacy specifications carried over from a totally different project a decade ago.
Oh, wow.
Yeah. And then add in conversational assumptions made by senior engineers over coffee and broad industry standards that were written by committees to apply generally, rather than to this specific design moment.
So requirements management has fundamentally shifted.
Exactly. It's shifted from a documentation task into this overwhelming information synthesis problem. The engineer's tasked with taking these scattered, often contradictory signals and somehow forging them into a coherent design intent.
And the cognitive load of juggling all those narrative statements, conditional data from suppliers, massive volumes of broad regulatory standards, it forces a survival mechanism.
Because gathering and synthesizing this information is just so overwhelmingly fragmented, teams default to copying and pasting old requirements.
Just to save time.
To save time and mitigate immediate risk, they grab the spec sheet from the last successful project and just apply it to the new one.
Assuming that if it worked then, it'll work now.
Right. And Autodesk notes that this reliance on precedent leads directly to two distinct failure modes in requirements packages.
Okay, what are they?
Well, sometimes the package is too thin, meaning it contains high-level aspirations without any measurable criteria for success. But much more commonly, and this is highly relevant to our focus today, the package is too dense, but poorly grounded.
Meaning it's just bloated.
Exactly. It becomes bloated with hundreds of hyper-specific statements and constraints, but the logical connections linking those constraints to the actual needs of the current project are weak, duplicated, or just entirely missing.
And that brings us to a concept in the sources that I found absolutely brilliant, the excellent attendance of old specifications.
Oh yeah, that's a great concept.
I mean, an industrial process can just hum along perfectly, checking all the boxes, passing every single quality audit, while the original requirement governing that process has become totally obsolete.
But the specification has excellent attendance simply because it gets copied onto every new project.
Every new CAD drawing, every new request for, quote, long after its original purpose has evaporated.
Right. A tolerance stays tight, a validation test duration stays long, physical packaging stays heavy, all because the spec was inherited, approved once, and is now treated as immutable geological fact.
Immutable geological fact, I love that. But if a process is stable and passing inspections, why mess with it? I mean, isn't it safer to just leave the old spec in place?
Well, you'd think so, but organizations are structurally designed to foster this exact behavior. Corporate hierarchies, change control boards, quality management systems, they're all highly optimized to catch and penalize unauthorized changes.
So if an engineer wants to fix it,
If they want to remove a legacy requirement or loosen a tolerance,
yeah,
they have to initiate a massive bureaucratic process.
right.
They have to run risk assessments, present empirical data, gather signatures from multiple departments, all just to prove that relaxing the spec won't cause a catastrophic failure.
But conversely, keeping a redundant, overly strict requirement
Requires zero justification. It just requires a signature to proceed. So organizations rigorously interrogate innovation, but they almost never question accumulated caution.
accumulated caution. That is the perfect term for it.
It really is.
It's the equivalent of wearing a heavy-duty offshore life jacket while standing in a puddle, simply because you were required to wear one while sailing in a hurricane last week.
Exactly. And taking the life jacket off requires filling out a 20-page risk assessment form, so you just keep wearing it in the puddle to avoid the paperwork.
The U.S. Department of Energy actually provides a highly practical example of this exact dynamic.
Yeah, regarding compressed air systems in manufacturing facilities.
Right. The DOE issues specific warnings that compressed air quality should only reflect the dryness and contaminant levels required by its specific end use.
Because compressing air and stripping it of moisture is a highly energy-intensive thermodynamic process.
So if a facility treats its central air supply far beyond the necessary dryness just to meet a broad blanket specification, they are burning massive amounts of electricity.
And wearing out their compressor equipment for absolutely zero functional gain. What's fascinating here is how perfectly this applies to everything else.
Yeah, if a pneumatic drill on the manufacturing floor operates perfectly fine on standard, somewhat dry plant air, but the central system is working overtime to supply hospital-grade, ultra-dry, totally oil-free air to the entire building just because one small lab space requires it.
That is a catastrophic waste of capital.
It really is.
The DOE's compressed air warning is the perfect mechanical metaphor for overspecification. Filtering the air beyond the required condition technically makes it cleaner, but that additional cleanliness adds no useful value to the pneumatic drill.
So a specification can be perfectly controlled. It can pass every single internal audit with flying colors, but it can be completely controlling the wrong variable.
Exactly.
Let's transition from the thermodynamics of air compressors to the brutal economics of physical metalwork.
This is where it gets really tangible.
Because inherited caution manifests physically on the manufacturing floor, and the financial consequences are staggering.
we really need to look closely at the exponential cost of precision, specifically regarding manufacturing tolerances.
So when engineers dictate tolerances, they are defining the absolute allowable margin of error in the physical dimensions of a manufactured part.
And the instinct, driven by that accumulated caution we talked about, is to default to the tightest possible tolerances. Tighter feels intrinsically safer.
It feels like higher quality engineering, right?
It does. But data from Modus Advanced, they're a manufacturer, specializing in precision components, reveals a brutal reality. The cost curve for tightening tolerances is not linear. It is sharply exponential.
Right, so if an engineer moves a design from a standard rough machining tolerance, say 0.030 inches, down to a precision tolerance of 0.001 inches, the cost of that part doesn't just increase by a few percentage points.
No, it quadruples.
4 times.
Yeah, and if they push that specification even further into the realm of ultra-precision, down to 0.0001 inches, the cost can multiply by 24 times compared to the standard baseline.
24 times. That is wild. We really have to break down the physical reality of the machining process to understand why that cost curve just explodes like that.
Well, when you demand a tolerance of 1/10,000th of an inch, you are fundamentally altering the physics of how that part is made. A machinist can no longer just load a block of aluminum into a standard CNC mill and let it run.
Because the process becomes highly iterative.
Exactly. The heat generated by the cutting tool causes the metal to thermally expand. So the machinist has to cut, stop, let the material cool, measure it, adjust the tooling offsets, and then cut again.
And they require highly specialized, incredibly expensive cutting tools that wear out faster.
And the quality control process shifts from a quick dimensional check on the shop floor with calipers to a comprehensive, time-consuming protocol using coordinate measuring machines inside a specialized, temperature-controlled metrology lab.
So you're paying for longer machine time, more expensive tooling, highly paid metrology technicians, and vastly higher rejection rates.
All for a tolerance that might not even be necessary.
And the physical reality of those metal machining tolerances becomes totally absurd when engineers blindly apply them to flexible material.
Oh, we see this constantly with converted parts like die-cut rubber gaskets or elastomeric seals.
Applying an ultra-tight metal machining tolerance to a flexible rubber gasket is literally like trying to use a highly calibrated laser micrometer to measure the dimensions of a plush foam mattress.
That is exactly what it's like. You are applying the rigid rules of metallurgy to a material that is designed to compress and deform.
Modus Advanced highlights the specific manufacturing chaos that this causes, right?
Yeah, they do. Converting processes like water jet cutting or rotary die cutting, they possess inherent tolerance capabilities dictated by the physics of the machine and the elasticity of the material.
Like with a water jet, it uses a high-pressure stream of water and a brace of garnet to erode material.
And as the stream penetrates, it naturally loses energy and spreads slightly, creating a tiny amount of kerf and taper.
So when an engineer ignores those physics and demands a tolerance of plus or minus 0.004 inches on a water jet process, that naturally and consistently produces plus or minus 0.005 inches.
They trap the manufacturer in an impossible mathematical corner.
Because the manufacturer can't alter the fundamental physics of the water jet stream to make it more precise than the machine allows.
Exactly. So to achieve statistical compliance and deliver an order of, say, 1,000 parts that fall within that unnecessarily tight 0.004-inch window, the manufacturer is forced into a strategy of intentional overproduction.
Wait, intentional overproduction, what does that mean?
It means they might have to cut 1,300 parts, measure every single one, isolate the parts that randomly fell into the tighter dimensional window, and throw the remaining 30% straight into the dumpster.
30% of perfectly good material.
Just wasted. And the labor required to measure all those parts skyrockets.
And the ultimate tragedy is that this massive expenditure provides zero functional benefit. I mean, the entire purpose of a rubber gasket is material compliance. It's supposed to squish, deform, and fill the microscopic gaps between two mating metal surfaces.
Right. The material's natural elasticity easily compensates for manufacturing variations.
So the most expensive tolerance on a drawing is almost always the one that fights the natural physics of the material without providing any functional improvement.
That's a great way to put it. And this phenomenon of precision acting as a penalty, it extends deep into the medical device industry, too.
Oh, really?
Yeah, we see a massive issue with the over-specification of internal components, specifically bearings.
Bearings. Okay. Let's unpack this. The medical device sector operates under intense regulatory scrutiny, obviously, so the psychological drive toward that accumulated caution has to be stronger here than almost anywhere else.
Absolutely. Engineers designing medical equipment consistently fall into the trap of over-engineering the internal motion components. They frequently demand bearings with incredibly high AB key ratings.
ABEC ratings being the industry standard, measuring the dimensional precision and run out of a bearing, right?
Yes, a higher ABIC number means the bearing is manufactured to tighter microscopic tolerances, which allows it to spin at incredibly high RPMs with minimal vibration.
So engineers designing a standard laboratory centrifuge or a hospital imaging machine will often specify ABEC 7 or ABEC 9 bearings.
Or they demand bearings with extreme dynamic load capacities engineered for aerospace applications.
But if I'm designing a hospital imaging machine, the scanning ring rotates smoothly and steadily. It is not a jet turbine operating at 30,000 RPMs under massive thermal stress.
Exactly. Specifying an aerospace-grade bearing for an imaging machine doesn't make the machine take better pictures, and it doesn't extend the life of the machine in that specific operating environment.
It just radically drives up the unit cost.
But the cost is only the secondary problem here. The primary problem is what it does to the company's operational resilience.
Oh, how so?
Well, by demanding hyper-precise, extreme-load aerospace bearings, the engineering team has inadvertently locked their manufacturing operation into a highly fragile, boutique supply chain.
I see. Because standard ABEC 1 or 3 bearings are produced by the millions and sit on distributor shelves globally.
Right. But ABEC 9 bearings are specialty items. They're often manufactured in small batches with incredibly long lead times. So if there is a global supply chain hiccup or disruption in specialty steel availability, those specific bearings vanish from the market.
Okay, let's unpack this irony, because it is painful. The engineer overspecifies the bearing because they want to guarantee the medical device is robust and reliable.
But by choosing a boutique component, they introduce a massive operational vulnerability.
Right. A hospital could be waiting 6 months for a life-saving imaging machine because the manufacturer's assembly line is completely paralyzed, waiting on a shipment of space shuttle-grade bearings that the machine never actually needed.
That's the trap. True engineering isn't just calculating the maximum theoretical stress limit of a part. It requires considering the integrated system, component availability, supply chain resilience, total cost, and realistic performance demands.
So tighter physical tolerances generate micro-level waste, like throwing away 30% of your rubber gaskets.
Yeah.
But over-specifying how a system is physically structured and controlled can trigger macro-level paralysis.
Exactly. And this requires us to examine how we define interfaces and design for future flexibility.
We can observe this perfectly by analyzing the pitfalls of defense procurement, right?
Yes, and the principles of flexible architecture in industrial automation.
Let's look at the defense sector first. We've got this striking case study from A&J Manufacturing. They have decades of experience building electronic enclosures for military applications.
The A&J Manufacturing case study is a masterclass in the dangers of the fragmented copy-paste requirements process that Autodesk warned about.
So A&J received a request for, quote, an RFQ to design and build a server rack that was destined to be installed inside a ground mobile program.
Right. A vehicle driving on land.
But the specifications explicitly demanded continuous salt fob resistance, IP67 water immersion sealing, and shock resistance capable of withstanding naval gunfire.
Which translates to surviving a 20G impact across multiple axes?
For a server rack?
Yes. This server rack was engineered to be bolted into a climate-controlled, air-conditioned vehicle shelter operating in the continental United States.
It was never going to be exposed to corrosive ocean salt spray.
Never.
It was never going to be submerged under a meter of water, which is what IP67 testing requires.
Nope.
And it was certainly never going to be subjected to the concussive shock wave of a battleship firing its main battery.
But because those hyper-specific environmental extremes were written into the RFQ document, they became absolute mandates that drove massive structural decisions.
But wait, if I'm a defense contractor, shouldn't I dictate exactly how the rack is built to ensure it survives?
You would think so. But to meet those irrelevant specs, A&J had to design extensive EMI and environmental gasketing, utilize heavy sealed military connectors, and heavily reinforce the structural mounting just to survive the 20G shock tests.
And when pressed, the military program office openly admitted that they had just copied the environmental specification package from a previous airborne and naval effort.
They operated on the assumption that making the rack universally survivable was inherently safer.
And the real-world result, a 40% cost premium, the necessity of incredibly expensive qualification testing, and a 2-month delay in delivering the equipment.
All for testing protocols that offered zero operational value to the troops on the ground.
This just highlights a critical failure in how requirements are written.
It does. There's a massive operational difference between specifying performance and specifying implementation.
Can you break that down?
Sure. Specifying implementation means the customer dictates exactly how the manufacturer must build the product. For instance, the spec might read, install 4 specific Berry 11127 Y-rope isolators at the base corners using 632 stainless fasteners.
That's really specific.
Extremely. When a customer does this, they're doing the manufacturer's engineering for them, and they're locking the project into a rigid, predetermined supply chain.
Okay, so what's the alternative?
If the customer instead specifies performance, they dictate what the product must achieve, leaving the methodology to the experts. The spec should read, the rack structure shall withstand a 20G 11 millisecond half-sine shock pulse with no permanent structural deformation.
Which allows A&J's engineering team to use their expertise to determine the most cost-effective, readily available method to absorb that shock.
Exactly. And exactly the same principle applies to raw material call-out.
Yeah, defense RFQs often feature ambiguous material requirements.
All the time. A document might simply state aluminum construction.
Okay, what's wrong with that?
Well, the customer, focusing on weight reduction for an aerospace application, implicitly assumes this means high-strength 7075 aerospace aluminum.
Okay.
However, the supplier, looking at a ground-based application and focusing on cost and manufacturability, interprets aluminum as standard 6061 commercial aluminum.
Which is very different.
Very.
Yeah.
6061 is highly weldable and cost-effective, but it lacks the tensile strength of zinc alloyed 7075. Both are technically aluminum, but this ambiguity leads to a massive 30% cost delta.
And probably structural failures during testing and the total rejection of the first article builds.
Yep. The solution is for the customer to specify the required physical property, such as panel deflection under a 5 psf pressure load shall not exceed 20.020 inches.
And allow the manufacturer to optimize the specific material alloy and gauge to hit that target efficiently.
Exactly.
That distinction between implementation and performance is just as critical in the digital realm, isn't it?
Oh, absolutely. Industrial automation and machine building face a very similar dilemma.
How does an engineering team select an automation platform that keeps a machine financially viable and simple today, but retains the technical capacity to adapt to new requirements tomorrow?
Carl Walker at Beckhoff Automation provides some deep insight into this challenge.
Right?
Machine builders are constantly navigating this precarious balancing act. If they over-specify the control architecture from day one, installing top-tier industrial PCs, highly complex motion controllers, and massive I/O racks for a machine that currently only performs simple, repetitive tasks, they destroy the machine's upfront cost competitiveness.
They extend the software commissioning time, require significantly larger electrical cabinets, and force the end user to stock highly expensive, complex spare parts.
They're basically forcing the customer to buy the 180-mile-per-hour engine just to drive in the school zone.
But the danger on the opposite end of the spectrum is equally severe, right?
It is. If the engineering team select a highly rigid, ultra-basic economy PLC platform just to save money on the initial build, they create a technological dead end.
Because when the end user's production requirements inevitably evolve next year, say they need to add a vision inspection system or integrate the machine with a cloud-based ERP system, that basic controller is fundamentally incapable of handling the data load.
And then the customer is paralyzed. The only solution is to rip out the entire hardware platform, discard all the original programming, and redesign the control architecture from scratch.
The dreaded rip and replace.
Yeah. But the way out of this trap is not choosing between maximum performance and rock-bottom rigidity.
It's adopting a truly scalable automation architecture.
Historically, automation suppliers segmented their product lines into distinct, incompatible families. Upgrading from a basic controller to an advanced controller required learning an entirely new engineering software environment.
Which is a huge pain.
Huge. But Beckhoff Automation advocates for keeping logic control, motion control, and safety protocols all within one unified software environment.
Using tools like TwinCat software and EtherCAT communication networks.
Yes. With a unified architecture, a machine builder can right-size the hardware for the exact need of the machine today.
They can start by installing a highly economical servo drive, like the Beckhoff AX1000, to handle basic point-to-point positioning tasks.
Because it is small, cost-effective, and perfectly matched to the immediate requirement.
But crucially, because the underlying twin-site software and the EtherCAT communication bus are infinitely scalable, the machine is not technologically trapped.
Right. When the machine's requirements inevitably expand, the engineering team can seamlessly introduce a high-performance industrial PC to the network to handle complex kinematics or heavy data processing.
They don't have to rewrite the core machine logic or rip out the existing drives. The software architecture scales organically alongside the physical machine.
They retain total flexibility for future demands without paying the massive upfront capital penalty of overspecifying the hardware on day one.
Okay, so we've analyzed how right-sizing prevents waste in metal tolerances and digital control architectures. But the psychological barrier to right-sizing becomes intensely rigid when we move into environments where human safety and strict federal regulations govern the process.
Cleanroom construction and pharmaceutical packaging are prime examples of this.
Because the stakes in these industries are literally life and death, so the engineering culture's fear of challenging a specification is astronomical. FDA and GMP compliance basically terrifies companies into over-specifying.
Patient safety is non-negotiable, of course, but as ACH engineering clearly illustrates, failing to right-size cleanroom classifications does not actually enhance safety.
It just acts as a massive multiplier for unnecessary capital and operational expenditure.
To really grasp the scale of this waste, we have to look at how cleanrooms are classified using the ISO system. The ISO classification dictates the allowable concentration of airborne particles per cubic meter of air.
An ISO 5 environment is exceptionally clean.
Yes. It is reserved for highly critical aseptic processing zones, like the exact physical location where sterilized liquid medicine is filled into vials.
And an ISO 7 or ISO 8 environment is progressively less clean, typically utilized for background operations, material staging, or the initial washing of components.
And the financial chasm between building an ISO 8 room and an ISO 5 room is breathtaking.
Constructing a standard ISO 8 cleanroom generally costs between $75 and $150 per square foot.
Which requires an HVAC system capable of performing 20 to 40 complete air changes per hour just to maintain those particle counts.
But stepping up to an ISO 5 classification requires a totally different approach to facility engineering.
It does. ISO 5 construction costs easily exceed $1,000 per square foot.
Over $1,000 a square foot.
Yeah, and the HVAC system must deliver a staggering 300 to 480 air changes per hour. To achieve that laminar airflow, 60 to 70% of the entire ceiling space must be covered with highly expensive HEPA filters.
So moving from $150 a square foot to over $1,000 a square foot is just the upfront capital hit.
It's exactly. Operating an HVAC system capable of 480 air changes per hour consumes an astronomical amount of electricity.
And the specialized HEPA filters require continuous, expensive certification testing and regular replacement.
The core issue arises when pharmaceutical engineering teams, driven by an abundance of regulatory caution, demand an ISO 5 classification for a process that fundamentally does not require it.
Right. It's a specific manufacturing step, like preparing products for a terminal sterilization process, only requires an ISO 7 background environment according to FDA guidelines.
Forcing that process into an ISO 5 room provides zero measurable increase in final product safety.
You've exponentially multiplied the energy consumption, the infrastructure complexity, and the maintenance costs for a purely theoretical margin of safety.
And our sources reveal this fascinating and honestly somewhat humbling thermodynamic reality about clean rooms.
Yeah, this part is wild. The physical design of the room and the filtration power of the HVAC system can really only do so much.
Because in an actively occupied clean room, human personnel generate approximately 70% of all airborne particulate contamination.
70%. So a single human being, even when standing relatively still, sheds hundreds of thousands of microscopic skin flakes and particles every single minute.
You can spend millions of dollars engineering a pristine ISO 5 clean room, but if your personnel gowning procedures are sloppy, or if operators are moving too quickly and generating turbulence,
the multi-million-dollar HVAC system cannot compensate for that human contamination.
the facility specification specification cannot out-engineer human behavior.
Demanding an ISO 5 facility when ISO 7 perfectly meets the regulatory standard is just the purest definition of accumulated caution driving bad economics.
Companies really must adopt risk-based classification selection.
Which means meticulously mapping the exact stage of the pharmaceutical process to the specific environmental grade required by the regulation.
Rather than lazily demanding the highest possible cleanliness rating across the entire floor plan.
And this exact same fear of challenging the regulatory status quo paralyzes the pharmaceutical packaging sector, doesn't it?
It does. Research from GEP's should-cost modeling indicates that packaging materials are a disguised, massive margin killer for pharma companies.
Packaging accounts for roughly 25 to 30% of total product costs.
And the raw plastic polymer makes up 50 to 80% of the cost of a molded packaging component.
The critical leverage point in manufacturing economics here is that 70 to 80% of a product's lifetime cost is permanently locked in during the conceptual design phase.
Think about that. Whatever polymer the design engineer selects on day one is what the procurement team will be forced to buy for the next 10 years.
Wow.
During the initial prototyping phase of a new medical device or pharmaceutical package, engineers frequently specify highly expensive advanced polymer grades, such as PEEK or glass-filled nylon.
They choose these materials because they represent the worst-case scenario protection.
Exactly. PEEK, for example, has incredible molecular stability and high heat resistance. It will survive almost any sterilization process or physical drop test.
But once the product moves into actual high-volume production, the data often shows that the extreme performance of PEEK is totally unnecessary for the everyday function of the package.
A standard, significantly cheaper engineering plastic like POM might perfectly meet all the verified functional and structural requirements.
It has great dimensional stability and impact resistance for normal use. So the obvious question is, once the engineering team realizes the standard plastic works perfectly fine, why don't they just switch the specification and save millions of dollars?
Because the regulatory friction required to change a validated material in the pharmaceutical or automotive industry is agonizing.
All right.
Requalifying a new polymer grade is not a simple paperwork update. It demands comprehensive production part approval process, or PPP, submissions.
It requires running entirely new stability testing cycles, submitting engineering changes to regulatory bodies like the FDA, and formally notifying global customers.
This requalification process can easily take 5 to 7 months of dedicated engineering time.
The bureaucratic friction is so intense that nobody is willing to champion the change.
So the legacy material approval persists, and the manufacturer silently hemorrhages margin on every single molded unit for the lifespan of the product.
So GEP argues that the only way to break this cycle of margin drain is by fundamentally shifting the procurement philosophy.
Traditional sourcing operates passively. A buyer sends an inherited specification to 3 suppliers and asks, "What will you charge us to mold this exact spec?"
But GPs should cost modeling forces an active forensic interrogation of the component.
It asks, what should this functionally compliant component cost if the material, the design, and the manufacturing process were optimized for reality rather than legacy?
Should cost modeling strips away the assumptions?
When procurement and engineering teams collaborate to build transparent cost models that break down the cycle time, the resin cost, and the machine overhead, they discover massive optimization opportunities.
Like, GEP highlights several high-impact examples in pharma packaging.
By questioning the fundamental format of a component, such as shifting from a rigid, heavy-walled plastic desiccant canister to a simple, flexible desiccant sachet, companies eliminate massive amounts of molded plastic.
And by using finite element analysis to optimize the resin thickness in caps and closures, shaving fractions of a millimeter off the wall thickness, pharma companies have consistently unlocked 20 to 40% sustainable savings.
Without compromising the barrier properties or safety of the package.
Okay, to fully internalize the financial gravity of right-sizing and challenging inherited specifications, we need to leave the sterile environment of the clean room and walk straight onto the gritty, intense floor of a metal foundry.
Oh, this is a great pivot. The casting industry provides some of the most visceral, easily understood examples of how rethinking a component slashes long-term expenses.
We have these insights provided by Tom Kaiser from Osco Industries, and it really serves as a practical masterclass in process efficiency.
Kaiser begins by destroying a very common illusion in procurement: The primacy of the unit price quote.
Right. If a buyer is solely focused on negotiating a few pennies off the quoted unit price of a raw casting, they're completely missing the forest for the trees.
To understand true manufacturing efficiency, you must calculate the total cost of ownership, or TCO. The unit price on the invoice is merely the visible tip of the iceberg.
The real financial bleed occurs below the waterline.
In hidden costs like freight density, sitting inventory carrying costs, rework, scrap rates, and the administrative overhead of managing complex supply chains.
Let's examine a very specific physical example Kaiser provides regarding weight reduction.
Okay.
An engineering team collaborated with the foundry to redesign a casting, optimizing the geometry to drop its overall weight from 13 pounds down to 11.5 pounds.
Now, to a layman, removing 1.5 pounds of iron doesn't sound revolutionary. It seems like a minor optimization.
But on the foundry floor, that 1.5-pound reduction triggers a massive systemic ripple effect.
Dropping weight isn't just about saving the cost of the raw iron or the energy required to melt it. The redesigned, later geometry physically altered how the metal flowed into the mold, which significantly reduced the time required to grind the finished part.
And crucially, the smaller physical volume of the casting completely transformed the shipping logistics.
Because the parts took up less volumetric space, the manufacturer could fit significantly more units into a standard shipping container, drastically slashing the per-unit freight cost.
All of these operational compounding factors, triggered by a mere 1.5-pound reduction, lowered the total cost of ownership of that part by a solid 6%.
And the economics of grinding out on the foundry floor is where this gets exceptionally compelling.
Here's where it gets really interesting. Grinding is one of the most physically demanding, labor-intensive, and expensive secondary operations in the casting process.
Kaiser has a fantastic rule of thumb. Anytime you see grind marks on a casting, you're looking at dollars.
We can quantify that waste with basic math. If a foundry's fully burdened labor rate, including wages, benefits, overhead is $85 an hour, every single minute an operator spends holding an angle grinder to a casting costs the company $1.42.
But if the purchasing team and the design engineers collaborate up front, they can completely eliminate that cost.
By strategically redesigning the tooling to move the gate, that's the channel where the molten metal enters the mold away from the critical parting line, they can ensure the gate material snaps off cleanly during shank-out.
This eliminates the need for manual grinding to flush the surface. Kaiser cites a specific case study where eliminating that single grinding step skyrocketed production throughput from a sluggish 60 pieces an hour to a blistering 200 pieces an hour.
They more than tripled their production volume simply by changing the fluid dynamics of how the molten metal entered the mold. That is the staggering power of challenging the implementation of a specification.
And the casting industry struggles with the excellent attendance of obsolete specs just as much as aerospace does.
The persistence of annealing is a perfect example of this.
Annealing is a metallurgical heat treatment process. You take the cast iron parts, load them into a massive furnace, heat them to a specific temperature, and allow them to cool slowly.
Which alters the microstructure of the iron, making it significantly softer and easier to machine.
Right. And Kaiser points out that decades ago, annealing was absolutely mandatory. Castings were being machined on 40-year-old manual Bridgeport mills. Those old machines lacked structural rigidity, and the high-speed steel cutting tools of the era would shatter or wear out instantly if the iron casting was too hard.
But the manufacturing landscape has evolved. Modern machine shops are filled with massive, highly rigid CNC machining centers wielding advanced carbide and ceramic cutting tools.
These modern machines can chew through extremely hard cast iron without breaking a sweat.
In fact, if the iron is annealed and made too soft, it actually negatively impacts the modern machining process.
It does. Soft iron becomes gummy, it doesn't form clean chips, and it degrades the surface finish of the final part.
Yet, the annealing process frequently persists today out of sheer institutional inertia.
The requirement remains on the drawing. When you ask the procurement team why they are paying the foundry to heat treat the parts, the answer is invariably, that is the way it has always been done.
In one documented case study, simply challenging that assumption and stopping the obsolete annealing process dropped the cost of the casting from $16.73 down to $14.82 per part.
The customer saved nearly $2 per casting. entirely by eliminating a legacy process that was actually making the product worse for their modern CNC equipment.
You see the exact same logic applied to internal core design.
Many castings require internal voids, which are created by inserting a consumable sand core into the mold.
If an engineer is willing to eliminate that complex internal core for a small sleeve, even if doing so requires pouring slightly more metal to make the part solid, thereby increasing the raw material weight, they can easily save $2 per part in labor and tooling complexity.
But the absolute home run of right-sizing, the ultimate demonstration of using engineering to collapse supply chain complexity, is the strategic conversion of fabricated weldments into single-piece cast components.
Yes, the weldment conversion. We must detail this specific process because it acts as the perfect synthesis of everything we've discussed today.
Why are weldments so financially draining? And why does converting them to a casting radically alter the total cost of ownership?
Well, a weldment is a structural assembly created by taking multiple separate pieces of steel plates, tubes, gussets, and welding them together.
The fabrication of a complex weldment is an intensely inefficient process.
It requires purchasing multiple raw materials. It demands high precision cutting and bending of each individual piece.
The fabricator then has to build complex, expensive jigs and fixtures to hold all those individual pieces in perfect alignment.
Finally, the company must employ highly skilled, highly paid welders to manually join every single seam.
The labor costs are astronomical, but the physics of the weldment itself also introduce massive risks.
Because the intense, localized heat of the welding arc changes the metallurgy of the steel, right?
Exactly, creating heat-affected zones that are prone to cracking.
Every single weld seam acts as a potential stress riser and a point of failure, requiring rigorous, time-consuming ultrasonic or X-ray inspection to guarantee structural integrity.
By collaborating with foundry engineers to redesign that highly complex multi-piece welded assembly into a single poured cast part, an organization completely rewrites the economic equation.
The benefits are profound. You eliminate the massive expenditure on skilled welding labor.
The physical component gains incredible structural consistency because it is poured as a single homogeneous piece of metal, eliminating the stress risers associated with weld seams.
Lead times drastically compress because you are no longer managing a multi-stage fabrication and assembly process.
The quality control process is simplified because you have eliminated dozens of potential failure points.
And you vastly simplify your ERP system and logistics because procurement is now tracking and purchasing one single part number rather than managing the inventory for 12 different steel plates and brackets.
It is a strategic, system-wide victory hiding in plain sight.
These massive improvements all originate from a buyer or an engineer pausing the process and asking, why are we doing it this way? Can we collaborate with the supplier earlier in the design phase?
And this critical thinking applies to things as seemingly mundane as the cardboard boxes the parts ship in.
Packaging logistics are a massive, frequently ignored strategic cost center. Single-use, disposable, corrugated cardboard boxes represent a constant financial drain.
Kaizen notes that if a heavy-duty cardboard box costs 52 cents and you are shipping thousands of castings a week, that disposable expense destroys your margins.
But by analyzing the freight loop and switching to durable, returnable plastic tubs shipped via dedicated freight lines between the foundry in Atlanta and the machining center in Greenville, the packaging cost plummeted.
From 52 cents per part down to just 11 cents per part.
The exact same holistic thinking must be applied to how you select the molding line at the foundry. You have to match the manufacturing technology to the reality of your company's cash flow.
If a buyer only looks at the quoted unit price, they will always choose a high-volume automated line, like a Disomatic molding machine.
The Disomatic produces parts at lightning speed, so the per-unit cost is incredibly low.
But because it is designed for massive runs, the foundry will require a minimum order quantity of, say, 1,500 parts.
And if the customer only uses 100 of those parts a month, buying 1,500 parts means they are tying up $22,000 in capital, sitting as idle inventory on their warehouse shelves for over a year.
A strategic buyer will instead select a lower volume molding line, such as a Hunter machine.
The Hunter process is slower, meaning the quoted unit price per casting will be higher.
However, the foundry might only require a minimum order of 100 molds. The customer pays slightly more per part, but they only tie up $3,800 in inventory.
For an organization actively managing tight cash flow, deliberately paying a higher unit price to avoid trapping $18,000 in stagnant inventory is brilliant right-size procurement.
It proves the necessity of looking at the entire operational ecosystem, not just the isolated unit cost.
So we have thoroughly mapped the devastation of bad specifications, from the micro-level waste of water jet tolerances to the macro-level paralysis of defense procurement and cleanroom HVAC loads.
We have seen the incredible financial leverage gained by challenging those specs.
But how does an organization systematically implement this mindset? How do we ensure that questioning legacy specifications becomes a standardized organizational habit rather than relying on a rogue engineer's one-off heroic effort?
To build that systemic habit, we need to look at the historical roots of value engineering, or VE, as detailed by Gate Energy.
Value engineering is not just a euphemism for cheapening a product or haphazardly slashing costs, is it?
No, not at all. It is a highly structured, rigorous methodology that has been transforming industrial projects for over 75 years.
Value engineering has a fascinating origin story that perfectly illustrates its core philosophy. It traces back to Lawrence D. Miles, an engineer working at General Electric during the height of World War II.
During the war, GE and the broader American manufacturing base were facing severe, catastrophic shortages of critical raw materials and specific component parts. Assembly lines were grinding to a halt.
Traditional procurement strategies, which involved simply trying to find a cheaper supplier for the exact same specified part, were totally ineffective because the parts simply did not exist.
Lawrence D. Miles realized that trying to replicate the exact physical design was the wrong approach. He initiated a fundamental paradigm shift.
He forced his engineering teams to stop asking, how do we find this exact part or make it cheaper, and instead asked a totally different question.
What fundamental function does this specific component serve within the larger system, and what alternative materials or designs can reliably perform that exact same function?
That distinction is the entire secret to the methodology.
By separating the required function of the part from the historical physical design of the part, Miles unlocked massive innovation.
He realized the system didn't need the specific bronze gear, it just needed the rotational force to be transferred.
Once you define the function, you can explore entirely new ways to achieve it.
And that philosophy evolved into the formal value methodology.
When this structured analysis is applied during the front-end loading phase of major capital projects, before the CAD models are locked in and the concrete is poured, VE delivers an astronomical return on investment.
The Gate Energy data shows that formal VE studies frequently generate a 7-to-1 or higher return on the cost of the study itself.
It forces diverse teams of engineers, operators, and procurement specialists to break out of their silos, examine the systemic function of the design, and prevents them from prematurely converging on comfortable, bloated legacy solutions.
So how can you immediately apply the philosophy of Lawrence D. Miles to your own work today? The sources provide a highly actionable, brilliant diagnostic tool called the Recheck Loop.
It is designed to help you systematically examine inherited requirements without triggering organizational panic.
The beauty of the Recheck Loop is its low-friction approach. To begin, you do not select the most mission-critical, highly visible, controversial safety specification in your entire operation.
You pick one single, mundane specification that everyone follows perfectly, but no one can clearly explain why.
Here's how you execute the loop. Step 1. Write down the exact, literal requirement as it is currently documented in the quality manual or on the CAD drawing.
Step 2. Identify the actual human owner of that requirement. Who holds the authority to approve a deviation?
Step 3. Forensically trace that requirement all the way back to an actual end-use scenario, a specific customer need, or a concrete regulatory safety obligation. Define the precise physical function it is supposed to be performing.
And step 4. Compare the literal written specification to the reality of the current operating condition.
Does the environment today actually demand this specific level of stringency, or are we paying for a 20G shock rating on a server rack sitting in an air-conditioned office?
Exactly. And the ultimate goal of the recheck loops is not to blindly slash safety margins or indiscriminately loosen tolerances just to save a few pennies.
No, absolutely not. The ultimate goal of the recheck loop is the recovery of specification understanding.
If an engineering team traces a requirement back and confirms that it fundamentally protects human safety, ensures regulatory compliance, or guarantees system reliability, that requirement must be vigorously protected and preserved.
Deliberate, deeply understood protection is the hallmark of great engineering.
It is the unexamined inherited caution that breeds waste.
If a specification goes through the recheck loop and survives entirely unchanged, that is still a massive victory for the organization.
The specification is no longer a blind habit. The logical reasoning behind it has been recovered, documented, and understood by the current generation of engineers.
Let's take a breath and recap the incredible terrain we have covered today.
We started by examining the psychological burden of fragmented inputs and how the chaotic synthesis of scattered data leads directly to the copy-pasting of obsolete requirements.
We analyzed how demanding microscopic 10,000th of an inch tolerances on metal CNC machines or forcing rigid specifications onto flexible water jet gaskets creates exponential cost curves and massive statistical waste.
We dissected how overspecifying internal components like medical centrifuge bearings severely threatens global supply chains.
We analyzed the defense sector to show how indiscriminately copying airborne naval requirements onto ground vehicles causes operational paralysis, and we underscored the vital necessity of defining performance targets rather than dictating implementation methods.
You saw how utilizing scalable, unified automation architectures like Beckhoff's TwinCat allows machine builders to prioritize future flexibility without overcapitalizing the initial build.
We've entered into the high-stakes environment of the pharmaceutical cleanroom to observe how demanding an ISO 5 classification when the process only requires an ISO 7 balloons construction costs from $150 to over $1,000 a square foot.
While completely failing to address the primary source of contamination, human personnel.
We learned from the foundry floor how challenging unit price illusions, eliminating legacy habits like metallurgical annealing, and converting highly complex, labor-intensive weldments into homogeneous cast parts can radically revolutionize an organization's total cost of ownership.
Overspecifying is a silent, systemic margin killer.
It is born not from a desire for quality, but from inherited caution, fragmented data, and a fundamental lack of systemic understanding.
By utilizing the structured philosophy of value engineering and deploying the diagnostic recheck loop, organizations can shift their focus from legacy compliance to actual functional performance.
They can reclaim control of their specifications and finally right-size their operations for the real world.
Absolutely.
I want to leave you with a final provocative thought, directly inspired by the Autodesk research regarding the chaotic front end of engineering.
We are currently moving at breakneck speed into an era where artificial intelligence and large language models are being deeply integrated into engineering, procurement, and design workflows.
The immediate danger is that organizations will utilize AI simply to write better-sounding, highly polished, grammatically perfect, bad specifications.
We run the risk of using incredibly advanced AI tools merely to generate the wrong requirements much faster.
But what if we flee that paradigm?
What if we utilize these powerful AI synthesis tools not to generate definitive answers, but to mercilessly expose our organizational blind spots?
What if the future of engineering management isn't about producing massive, polished specification documents, but about creating a highly detailed map of exactly what we do not know?
AI could be used to ingest decades of fragmented inputs, identify the contradictory standards, flag the obsolete legacy requirements, and surface the hidden tensions between different operational goals.
If we can use technology to create a structured, visible map of our own uncertainty, we can finally stop managing accumulated caution, and we can start asking the right functional questions.
That represents a profound, necessary shift for the industry. It is the evolution from generating data to actually synthesizing understanding.
So the next time you are reviewing a design drawing, evaluating a vendor quote, or signing off on a quality document, think about that 180-mile-per-hour sports car parked in the 30-mile-per-hour school zone. Look critically around your own operation. Find your own 180-mile-per-hour legacy specification and put it through the recheck loop. Thank you for joining us on this deep dive. Go question a legacy spec today.